Okay, example 3. We want to know the magnitude of the force exerted on Q3 by Q1 and Q2. And this is going to have to do with a 3, 4, 5 triangle here. So we'll have 3 centimeters and 4 centimeters as the sides of the right triangle. I'm going to leave this distance as a question mark for now, even though I've already spilled the beans and said it's a 3, 4, 5 triangle. I want to show you the formula that you use to find that side, which I'm sure you guys are familiar with. And then this is let's just say 5 coulombs, 3 coulombs, -2 coulombs. And once again, we want to know what is the net force on 3. So we'll have to figure out what that is. And I'll draw in some forces here. So the -2 coulomb charge is going to attract the Q3. So the force that 2 exerts on 3 is drawn here. And the 3 coulomb charge is going to repel Q3. So the force that 1 exerts on 3 is drawn here. And so we already basically know that when we go to make our free body diagram, it's going to look something like, when we change the colors, we'd have something like F13, F23, and theta. And theta would just be this angle here, which is alternate and interior to this angle. So that angle is going to be of interest in terms of solving this problem. So I'm going to make a list of knowns and unknowns. So knowns, unknowns, and equations. Obviously, we have that the force that one object exerts on another in terms of magnitude is 1/4 pi epsilon 0 times the absolute value of charge A times charge B all over the distance between them squared. Oops, I accidentally flipped this upside down here. We also know that we know the Pythagorean theorem. So we know if we have A, B, and C, that C equals the square root of A squared plus B squared, right? And if I look at unknowns, let's go back. Let's see. I don't know the forces. I don't know the net force. Don't know its magnitude or direction. I don't know theta. And I don't know this distance here, which is the distance from 2 to 3. So R23 is unknown. Force of 2 on 3, the 2 exerts on 3 is unknown. Force that 1 exerts on 3 is unknown. Theta is unknown. And neither do I know some of the forces in the x direction acting on it, some of the forces acting in the y direction, the magnitude of the sum of the forces, and I don't know the angle of the sum of the forces either, but I don't want to fit that in here, so I'm going to just leave it out. But then in terms of knowns, I know charge 1, charge 2, and charge 3. I also know the distance from 1 to 3, because that was drawn on the triangle. So the distance from 1 to 3 was 3 centimeters. And then my charges are 5, -2, and 3. So these are my knowns. So the easiest thing to get right now is R23. I know that R23 is the hypotenuse of this triangle here. So I just need to work that out, and I know the other two sides. And so to find R23, well, I know that I have a 3, a 4, and R23 here. So A is equal to 3, B is equal to 4 for centimeters. R23 is the square root of A squared plus B squared, which is the square root of 3 centimeters squared plus 4 centimeters squared, which is the square root of 9 centimeters squared plus 4 centimeters squared, which is 16 centimeters squared, sorry. Uh, 9 plus 16 is 25 centimeters squared. And then this is the square root of 25, square root of centimeters squared. That's 5 centimeters. So R23 is 5 centimeters. Okay, so next we need to find theta. Theta would be the most reasonable thing to go for here. So next we need to find theta. Theta would be the most reasonable thing to go for here. So to find theta, we're going to note that it is this angle in the right triangle. And we know that the tangent of theta is opposite over adjacent, which means that the tangent of theta is A over B. So theta is the tangent inverse of A over B. A is 3 and B is 4. So you have the tangent inverse of 3/4. And I just need to figure out what number that is. So I'm going to use my calculator. I'm going to do tangent inverse of 3/4. And I get 36.87 degrees. Make sure you are in degree mode. And in fact, I would just double check and make sure that you get that same number. Because if you don't, the chances are you are not in degree mode. Okay. Next, we can start to find the magnitudes of the forces. So we can find F23 and F13. F23, the magnitude of the force that 2 exerts on 3, is 1 over 4 pi epsilon naught times the absolute value of charge 2 times charge 3 divided by the distance between charge 2 and 3 squared. 1 over 4 pi epsilon naught is just Coulomb's constant, so that's 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Let's see what these other values are. Charge 2 is -2, charge 3 is 3, so I have -2 times 3, and those units were just coulombs, so I'll go ahead and put that in there. And I notice that R23 is 5 centimeters. The absolute value bars will kill the negative on the -2, so I can drop that in my next line. So now what I have is 8.99 times 6 all over 25 times 10 to the -4. Where did the 10 to the -4 come from? That came from the centi. Remember that centi is 10 to the -2. So when I square that, I have to square the centi as well. The units are Newton meter squared for Coulomb squared from Coulomb's law. I get a Coulomb squared from the charges, and a meter squared from the R. Meter squares cancel, and the Coulomb squares cancel. So now I have 8.99 times 6 divided by 25. Go ahead and work that out. And I get 2.1576. And then the order of magnitude is going to come upstairs as a positive power. And so I have 2.1576 times 10 to the 4th newtons. And there's a tremendous number of newtons, and the reason we're getting such a big value is because we are using the charges that are as big as multiple coulombs. And a coulomb is a tremendous amount of charge. Now we'll focus on the force that 1 exerts on 3. And it's just Coulomb's law formula all over again. And I'll write 2.1576 times 10 to the 4th newtons. Okay, that's a 7. Okay, so for F13, I need Q1, Q3, and R13. So it's 5 coulombs, 3 coulombs, and 3 centimeters. 5 coulombs, 3 coulombs, 3 centimeters. And my 1 over 4 pi epsilon naught is just Coulomb's constant. So that's just going to be 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Okay, working this out, I have 8.99 times 5 times 3 all over 9 Newton meter squared per Coulomb squared times Coulomb squared over meter squared. And the 9 gets a 10 to the negative 4th. Okay, so what's going on? So the 9 is just the 3 squared, and the 10 to the negative 4th is just from the centi. When you square a 10 to the negative 2, you get 10 to the negative 4th. This unit is from Coulomb's constant. These units are from these guys and that guy, respectively. And now I just have to do the arithmetic. Coulomb squareds cancel, meter squareds cancel. If I round things a bit, I'll notice that 8.99 is really close to being the same as 9. So I'm going to approximate 8.99 as being 9 and just cancel these out. And I'm left with 15 times 10 to the 4th newtons. And I can get away with that rounding because I only have one significant digit on my charges anyway. All right. Now it is time to compute the net force. So if you recall, this is our free body diagram for charge 3. And I can use that to compute the net force and to go ahead and insert numbers in for the forces that I found. Okay. So here's X and Y. Here is the force that charge 1 exerts on charge 3. Here is the force that charge 2 exerts on charge 3. And here is theta. I can make a force chart where I fill in the components for these different forces. So for the force that 1 exerts on 3, you can see that the force just points directly upwards. It doesn't point sideways at all. That means the x component is 0, and the y component is positive and equal to the entire magnitude of that vector. For the force that 2 exerts on 3, you can see that the x component must be positive and the y component must be negative because it points to the right and down. Any force that points to the right has a positive x component. Any force that points down has a negative x component. Then the magnitude of, well, let me pause for a second. So Now I need to get the components, and the way to do that is to form a right triangle where the force vector itself is the hypotenuse. So I'm going to drop a triangle down to the x-axis like this, and I now have a hypotenuse and an angle, and the x component is the sideways piece of that triangle. So if I change my color here, this is the x component, and this is the y component. The x component, or the component in general, let me just write the x component. The x component is going to be the magnitude of the vector, plus or minus, times either the sine of the angle or the cosine of the angle. And whether we use sine or cosine for the trigonometric function depends on whether that component is opposite to or adjacent to the angle. If you recall from trigonometry, cosine of theta is adjacent over hypotenuse, and sine of theta is opposite over hypotenuse. So if our component is adjacent, we'll use cosine, and if it's opposite, we'll use sine. Looking here, you can see that the x component is adjacent to the angle, because that side is actually touching the angle. So we will use cosine for our x component. And then our y component in this case will be basically the same formula where you choose sine or cosine depending on whether it's adjacent or opposite. If you look at the y component, to get to the y component from that angle, you have to cross through the interior of the triangle. And in that case, it is the opposite side. So we'll go with sine for that case. So this will be f(2,3) cosine theta. This will be f(2,3) sine of theta. Now I can start to compute the net force, because the net force is just the sum of the components. It's computed by summing the forces, which we can do component by component. So the sum of the forces in the x direction is just going to be 0 plus f(2,3) cosine of theta. Or in other words, it's just equal to f(2,3) cosine of theta. And the sum of the forces in the y direction is f(1,3) minus f(2,3) sine theta. Now I can plug in numbers. So if I go back, I can find out what numbers we had for these guys. So f(2,3) was 2.1576. 1576 times 10 to the 4th newtons. The angle for theta was 36.87 degrees. And so this is also 2.1576 newtons, 36.87 degrees. And f(1,3) was 15 times 10 to the 4th newtons. So now we can start computing things. I'll start with the sum of the forces in the x direction. So I need to multiply f(2,3), which is 2.1576, times 10 to the 4th. I gotta multiply that by the cosine of 36.87 degrees. That's what I have for this whole value is let's see, 2, 3, 4, so 1.726 times 10 to the 4th newtons. And then if I go with some of the forces in the y direction, I first have to multiply f(2,3) times the sine of theta. So this will be 2.1576 times 10 to the 4th times the sine of 36.87 degrees. And so I get 1.2945 times 10 to the 4th newtons. And then I need to subtract that from 15 times 10 to the 4th. And what I get is 1.37, let's say 1 times 10 to the 4th. And of course, these are not, oh, sorry, not 10 to the 4th, times 10 to the 5th. And of course, these are not proper significant figures because I only have one significant digit in my actual values. But I'm just carrying extra decimal places so that I don't get intermediate rounding errors just due to the mathematical calculations. So I now have the sum of the forces in each direction. So these guys are checked off. I don't want to have to go flip back and write them down. And now I just need to figure out the magnitude of this net force and also the angle that it makes. So the angle of the net force. Okay. So the magnitude of the net force is obtained the usual way that you find the magnitudes of vectors. It is obtained using the Pythagorean theorem. And so for these guys, I have 1 point. I'm going to go ahead and rewrite this force on the right to be in terms of 10 to the 4th. So I have 1.726 and 13.71. And now I need to square these and add them together. So 1.726 squared plus 13.71 squared is 190.94. Square root that. I get 13.8 newtons, which really, when we're down to 1 sig fig, is just 10 newtons. But so the final answer would be 10 newtons once I round for significant figures. And of course, I got to carry this order of magnitude. But I'm going to stick with the 13.8 if I have to use it again in further calculations. As far as the angle is concerned, both of my components had turned out to be positive, right? So what that means is that the resultant net force is actually somewhere out here in the first quadrant. You can see why that should be. Based on my picture, you wouldn't expect that, but actually this vertical vector is actually in reality much longer than what I drew. So it actually should be even bigger than that. Anyway, so the net force is in the first quadrant. The angle for the net force is this guy right here. And so to compute that, I would just need to construct a triangle where I recognize that this is the sum of the forces in the y direction, and this is the sum of the forces in the x direction. So to get the angle for the net force, that's right, okay, the tangent of the angle for the net force is the sum of the forces in the y direction divided by the sum of the forces in the x direction. That means the angle for the net force is the tangent inverse of that ratio. That's the tangent inverse of what exactly? Well, 13.71 to 1.726. In this case, I don't have to worry about units or the order of magnitude because they would cancel out being the same. So I have 13.71 divided by 1.726. That's 7.94. I want the tangent inverse. What is that? 82.8 degrees. And so my net force vector ends up pointing into the first quadrant. It makes an angle of 82.8 degrees, so it's actually much steeper than what I'm drawing here. And it has a magnitude of approximately 13.8 degrees. Or 13.8 newtons, sorry. And that is the answer to the problem. Trajectory will experience a force which points up and to the right, 13.8 newtons. And this should kind of make sense because that positive charge exerts such a stronger force on it that it is going to go up rather than down towards the negative charge. Okay, that's the problem.